Welcome to this lesson on one of the most important principles in experimental science, the proper treatment of unusual or anomalous data points. Today we're going to explore why removing outliers just to make your curves look smooth can be scientifically disastrous. When you plot experimental data and see points that don't fit the trend, there's often a strong temptation to simply remove them. After all, wouldn't the data look so much cleaner without those pesky outliers? Here we see typical experimental data. Most points follow a nice linear trend shown in green, but there are two red outliers. The temptation is to simply delete these red points. But this approach is scientifically dangerous and can lead you to miss genuine discoveries. Let me explain why. When you encounter data points that deviate from your expected trend, there are fundamentally two possibilities you must consider. Possibility 1. The deviation is due to random noise, measurement error, or some temporary glitch in your experimental setup. This is what we call statistical fluctuation. Possibility 2. The deviation represents a real physical effect. It could be the first sign of a phase transition, an instability, a new regime of behavior, or even a completely unexpected mechanism. The critical question is, how do you distinguish between these two possibilities? And the answer is definitely not to simply delete the points you don't like. Let me give you a powerful historical example. In the 1980s, scientists discovered the Antarctic ozone hole. But here's the remarkable part. The data showing this depletion had actually been collected years earlier. Satellite instruments had been measuring ozone concentrations, but the data processing software was programmed to automatically reject values that seemed too low, assuming they were instrument errors. The algorithm was designed with the assumption that ozone concentrations couldn't drop below certain levels. So when the instruments detected extremely low values over Antarctica, the software automatically flagged them as errors and discarded them. It wasn't until ground-based measurements independently confirmed these low values that scientists went back to the satellite data and realized the anomaly was real. By that time, several years of critical data had been lost. This is a perfect example of why you should never automatically discard anomalous data. What looks like noise could actually be a groundbreaking discovery. So what's the proper protocol when you encounter unusual data points? Let me walk you through the scientific best practices. Step 1. Record absolutely everything. Every single measurement must be documented along with the complete experimental conditions at the time. Temperature, humidity, time of day, instrument settings, everything. Your lab notebook should contain every measurement, even ones you suspect might be problematic. Note your suspicions, but keep the data. Step 2. If you notice something unusual during the measurement, write it down immediately. Was there a power fluctuation? Did someone bump the table? Did the temperature change? Record it all. Step 3. This is crucial. If you get an anomalous point, don't just move on. Repeat that measurement under the same conditions. Do you get the same anomaly? This is how you test reproducibility. If the anomaly reproduces consistently, you've just discovered something real. If it doesn't reproduce, then you can be more confident it was noise or a temporary error. Even if it doesn't reproduce, you still keep the original data in your records. You just note that it was non-reproducible. Now let's talk about the proper statistical treatment of data. This is where error bars and fitting methods become critical. Every experimental data point should have error bars. These represent the uncertainty in your measurement. Without error bars, you can't properly assess whether a deviation is significant. Here's proper data presentation. Each point has error bars showing the measurement uncertainty. Notice this red point. Its error bar overlaps with the trend, so it's not necessarily an outlier. The standard error of the mean is sigma divided by square root of n, where sigma is the standard deviation and n is the number of measurements. This quantifies your uncertainty. When fitting curves to data, don't just use ordinary least squares blindly. Use robust fitting methods that can handle outliers without being completely dominated by them. Good, robust methods will fit the main trend while simultaneously highlighting which points deviate significantly. They expose the anomalies rather than hiding them. Use weighted fits when your data points have different uncertainties. Points with smaller error bars should have more influence on the fit than points with large error bars. The chi-squared statistic is the sum over all points of the squared deviation divided by the variance. This is the basis for weighted least squares fitting. For a good fit, you expect chi-squared per degree of freedom to be close to 1. If it's much larger than 1, your model doesn't fit the data well. If it's much less than 1, you may be overfitting or your error bars are too large. Let me give you a concrete example of how anomalous data can reveal real physics. Consider measuring the heat capacity of a material as you vary temperature. Imagine your data looks mostly flat at low temperature, then mostly flat at high temperature, but there's this huge spike right in the middle. Is that spike an error? That spike is actually extremely important. It could indicate a phase transition, like melting, boiling, or a magnetic transition. The heat capacity diverges at phase transitions. Heat capacity is temperature times the derivative of entropy with respect to temperature. At a phase transition, entropy changes discontinuously, causing heat capacity to spike. If you had simply deleted that spike point because it didn't fit your smooth curve, you would have completely missed the phase transition. You would have missed the most interesting physics in your system. Here's another scenario. Suppose you're measuring the position of a pendulum as a function of time, and most points follow a smooth sine wave, but occasionally you get wild deviations. You see nice periodic motion with a few points that seem completely random. Are these errors or real behavior? These deviations could indicate your system is transitioning to chaotic dynamics. At certain parameters, even simple pendulums can exhibit sensitive dependence on initial conditions. Or they could reveal nonlinear effects, resonances, or coupling to other degrees of freedom. These are all genuine physical phenomena that would be invisible if you smoothed them away. Now let's talk about how to properly document and report data with anomalies. This is critical for scientific integrity and reproducibility. In your figures, use different colors or symbols to mark data points that you consider atypical or questionable. Make them visible. Don't hide them. Even if you don't show every single point in your main figure, include the complete data set and supplementary material. Other researchers should have access to all your raw data. If you do exclude any points from your analysis, you must provide explicit, documented justification. Confirmed instrument failure, power outage during measurement, these are valid reasons. I just didn't like how it looked is not valid. Good practice provides concrete, verifiable reasons for exclusion. Bad practice relies on subjective judgment about what looks right. If you want to identify outliers objectively, use proper statistical tests rather than visual inspection. Let me show you some common approaches. The Grubbs test can detect a single outlier in a dataset. It calculates how many standard deviations the suspected point is from the mean. The Grubbs statistic G is the maximum absolute deviation from the mean divided by the standard deviation. If G exceeds a critical value, the point is statistically unlikely. For small datasets, the Dixon-Q test is often used. It compares the gap between the suspected outlier and its nearest neighbor to the range of the data. The Chauvenet criterion rejects points that have a probability less than 1 over 2n of occurring, where n is the number of measurements. It's a probability-based approach. Here's the critical point. Even if a statistical test identifies something as an outlier, that doesn't automatically mean you should delete it. It means you should investigate it further. Let me give you an analogy to help you think about anomalous data. Imagine you're a detective investigating a case, and you find a clue that doesn't fit your current theory. A bad detective throws away clues that don't fit their preconceived theory. A good detective investigates every clue thoroughly and is willing to revise their theory. Anomalous data is exactly like a clue that doesn't fit your current theory. It might be meaningless, or it might be the key to solving the entire puzzle. Your job as a scientist is to investigate thoroughly, not to ignore what doesn't fit. The most important discoveries often come from investigating what doesn't make sense. Let me walk you through a numerical example inspired by the discovery of high-temperature superconductivity. Imagine measuring electrical resistance as a function of temperature. Most of your data shows resistance increasing linearly with temperature, as expected for a normal metal. But below a certain temperature, resistance suddenly drops to essentially zero. At high temperatures, the resistance follows the expected linear increase. This is normal metallic behavior due to phonon scattering. For normal metals, resistance follows this linear relationship where R0 is the resistance at 0 Kelvin and alpha is the temperature coefficient. But below 90 Kelvin, something dramatic happens. The resistance doesn't just decrease, it drops to 0 within measurement precision. Your first reaction might be to think the instrument malfunctioned. 0 resistance seems impossible. But this is exactly when you need to investigate further. Proper investigation reveals this is a superconducting transition. The material has entered a quantum state where it can carry current with absolutely no resistance. This is Nobel Prize level physics. For yttrium barium copper oxide, the critical temperature is about 90 Kelvin. This was revolutionary because it's above the boiling point of liquid nitrogen. Let's talk more broadly about how anomalous data can indicate new regimes of behavior or unexpected mechanisms. You might ask, what exactly constitutes a new regime? A new regime is when the physics governing your system fundamentally changes. A new regime occurs when different physical processes become dominant. For example, at high speeds, relativistic effects become important. At low temperatures, quantum effects dominate. Often, a new regime is signaled by the breakdown of an approximation you've been using. If your data suddenly deviates from theory, maybe the approximation is no longer valid. Classical mechanics works great for everyday objects. But at atomic scales, it completely breaks down. If you were measuring atomic spectra in the early 1900s, classical predictions would fail spectacularly. The Heisenberg uncertainty principle shows why. Delta x times delta p is greater than or equal to h bar over 2. This quantum mechanical limit has no analog in classical physics. If you had discarded the anomalous atomic spectra data because it didn't fit classical theory, you would have missed the entire quantum revolution. Let me summarize a practical workflow for handling your experimental data properly. Step 1. Record everything as you measure it. Don't wait until the end of the day. Real-time documentation prevents memory errors. Step 2. Plot your data as soon as possible, ideally in real time. This allows you to spot anomalies while you're still in the lab and can investigate. Step 3. If you suspect an issue, note it clearly in your records, but do not delete the data point. Your suspicion might be wrong. Step 4. If time and resources permit, repeat any measurements that seem anomalous. Can you reproduce the anomaly? Step 5. When analyzing, use proper statistical methods including error propagation, weighted fits, and outlier tests. Step 6. In your reports and publications, be completely transparent. Show all your data, mark anomalies clearly, and justify any exclusions explicitly. An important aspect of dealing with anomalous data is the role of replication. If your anomaly is real, other researchers should be able to reproduce it. Independent replication by other labs is the gold standard for confirming that an effect is real and not an artifact of your particular setup. If multiple independent groups cannot replicate your anomaly, that suggests it was likely an artifact specific to your setup or an uncontrolled variable. But here's the key point. You shouldn't discard anomalous data just because you haven't replicated it yet. Report it honestly, and let the scientific community help determine what it means. The cold fusion controversy of 1989 is an interesting case. Initial reports claimed anomalous heat generation that couldn't be explained by chemistry. Most replication attempts failed, suggesting the original results were artifacts. Even in controversial cases like this, transparency about all the data is essential. It allows the scientific community to properly evaluate claims and identify what might have gone wrong. Let me give you a more mathematical framework for robust data analysis that properly handles outliers. Instead of the mean, consider using the median for central tendency. The median is robust to outliers because it depends only on the middle value. The median absolute deviation, or MAD, is a robust measure of spread. It's the median of the absolute deviations from the median. For regression, you can use robust methods that minimize absolute deviation rather than square deviation. This reduces the influence of outliers while still fitting the main trend. This is L1 regression, minimizing the sum of absolute values. Compare this to ordinary least squares, which minimizes the sum of squares. M-estimators are a general class of robust methods that downweight outliers based on their residuals, but don't completely eliminate their influence. Let me conclude with some final thoughts and best practices that every experimental scientist should follow. First, maintain healthy skepticism about your own theories. Don't get so attached to your expected result that you ignore data that contradicts it. Remember that nature doesn't care about our expectations or our theoretical predictions. The universe is under no obligation to behave the way we think it should. Historically, the most important scientific discoveries often started as anomalies that didn't fit existing theory. X-rays, radioactivity, cosmic microwave background, all were unexpected. Document everything thoroughly. Future you, 6 months from now, trying to write a paper, will be extremely grateful that present you kept detailed notes. Don't work in isolation. Collaborate with colleagues and consult statisticians. Fresh eyes often catch things you've been staring at too long to see. From an ethics standpoint, never fabricate data, never falsify results, and never selectively omit data just because it doesn't support your hypothesis. This is scientific misconduct. Your reputation as a scientist depends entirely on your honesty and integrity. One instance of data manipulation can destroy a career. In conclusion, I want you to embrace the unexpected in your data. Those weird points that don't fit might be errors, but they might also be your ticket to a major discovery. Science advances not by confirming what we already know, but by carefully investigating what we don't understand. Anomalies are opportunities. Keep your full data set, document everything thoroughly, and investigate anomalies carefully with proper reproducibility tests. Use robust statistical methods that expose deviations rather than hiding them. Let the data speak for it. Report your findings transparently. Mark atypical data points clearly in your figures and provide full justification for any excluded data. Most importantly, stay curious. When something doesn't fit your expectations, that's not a problem to be swept under the rug. That's nature trying to teach you something new.